This is Sarah Brings with the Professor Podcast, the podcast of your professors, their research, and their academic lives here at St. Thomas. This week, we're delighted to have Thomas Secord, Associate Professor of Mechanical Engineering and Program Director of Masters of Science in Mechanical Engineering here at St. Thomas. Thanks for joining us.
Thanks for having me. I appreciate it.
Yeah, so to begin, could you start by telling us a little bit about yourself and your background and what led you to your current research?
Sure. So, as was said, my name is Tom Secord, and this is actually my 10th year at the University of St. Thomas. And before that, I was actually a full-time engineer at Medtronic here in the Twin Cities, working on implantable cardiac medical devices. And that was actually my first full-time job after graduate school. So backing up even further, I did my master's and PhD at MIT out in the Boston area. And then Minnesota is home for me, so I did my undergraduate degree in mechanical engineering at the University of Minnesota. So basically all my degrees are in mechanical engineering. I've always had a passion for that area of engineering, even going into college. So, I guess say that that's really what led me onto this path, was just some interest in mechanical engineering. And then in college, I was able to kind of zero in on an area of mechanical engineering that I would call controls, instrumentation, and robotics. So it's a sub-discipline of mechanical engineering. And that's what led me into my graduate program, was working in that area, finding research in that area. So I was very fortunate. I had a really great experience doing my master's and PhD at MIT in that area. I worked in a robotics research lab, and my advisor was, very well known within the robotics world. And so I just learned an immense amount about that, and that just further pushed me into this research area of controls and robotics and instrumentation. I'd say more broadly, just anything that moves in a novel way, and how we detect that movement is something that's just fascinating to me. So that's, the snapshot of kind of where I came from and where I am now.
Great. Could you give us kind of a brief overview on what you're currently working on and what that looks like?
Sure. So my most recent project is an NSF-funded research project that I'm working on in collaboration with some faculty at both Iowa State University and University of Florida. And that project, its main goal is to develop exterior systems for buildings that can make those buildings more efficient. So one term that's sometimes applied to this area is adaptive facades. So on the exterior of a building, you have, of course, the windows and the main structure, but then sitting, say, 1 foot out from that would be a facade that can reconfigure itself to either let more light in or block more light out. If it's a really sunny time of day and you don't want to heat up the building, say in the summertime, the facade can then close itself off. So the goal of the project, as I said, was to just look at existing systems, find ways to make them more energy efficient and maybe more versatile in the way that they can move and adapt to the environment. And it's been really fun because it's a collaboration between civil engineers at Iowa State and architects also at Iowa State, and then some industrial engineering-oriented folks and optimization-oriented folks at the University of Florida. So at St. Thomas, we basically bring the design side and the mechanical engineering side to figure out what are the realistic ways to make these mechanisms move and reconfigure. So
that's super interesting. Yeah. Are there any challenges you face when you're collaborating with other groups to try to tackle one research goal?
It has been definitely a learning experience. It's not without some challenges. Being at 3 different geographies, 2 different time zones is a little bit tricky to get meetings on the calendar and get everybody in the same place, even if it's on Zoom, is a little tricky. But that's the biggest thing, I would say. In general, the team is working great together. We had an on-site meeting over the summer in June, and that was great. It really kicked off the project, and we kind of set some goals for how we wanted to communicate, how regularly we wanted to meet, and those kinds of things. Not always easy, but that was probably the biggest challenge, was just getting that communication piece down.
Yeah. So for those of us that are a little unfamiliar for what research might look like for people who are doing engineering or robotics are in that kind of realm. What kind of tools do you use?
Yeah. I would say there's a number of different tools. Maybe the two big categories would be what I would call analytical tools, so how we analyze problems, but then also hardware tools. Like what do we do when we're actually building hardware? On the analytical side, there's software that we tend to use when it comes to like predicting how something might behave. I tend to use a software package a lot that's called MATLAB. A lot of what I need to do, I can essentially envision code for it. I'll write a program to maybe simulate something, and then that's essentially the transition into the hardware. It's like, okay, I've predicted how something is going to move or actuate or behave in a simulation program. Let me now translate it into the physical apparatus. And so on the physical side, in my research lab on South Campus, I have a number of what I would call actuators. So things that would move in different directions, and I can control their movement. And then I use a number of sensors, so things that detect how far something has moved. And there's a whole set of options to choose from. And I've, over the years, collected a pretty good variety of things that I can try in terms of both actuation and sensing. And the usual, lab equipment. So it's kind of looks a little bit like a mad science lab in there, where there's screens with waveforms, and there's essentially power supplies that power everything. And so there's a bank of electronics, and then our test setups are usually just on a typical lab bench. So,
are students involved in your research at all?
Yes, I had the good fortune of working with a couple great undergraduate students this summer, one of whom stayed on in the fall and is still continuing to work on the project I mentioned. And that's been great. I think it's always nice when they can get an experience outside the classroom that allows them to learn about both the analysis side and the hardware side in a way that they probably wouldn't encounter in class. Or if they do encounter it in class, it might be after when they encounter it in research. And so they're primed to fully understand that item or that topic when they hit it in the class.
Yeah. And I'm just curious, so with your current project, when all of that data is collected, your models are built, you have it laid out in a way that's digestible, who then will use that research?
Yeah, well, the hope is that there is a path to maybe even commercialization. Mm-hmm. It's not unheard of that some of these research projects do lead into some maybe startup company that takes this technology and really tries to bring it to market. So that would be the dream. I would say that if we do our job well enough and have solved the problem well enough, it makes the commercialization path easier and a little more visible to people that have that entrepreneurial spirit. Yeah. I myself didn't have that necessarily that bug of entrepreneurship that I really wanted to start companies and things like that. But that is typically how these research projects go, is if it's a well-done piece of technology, they can, there's a group of people that would be willing to commercialize it. That's how it ends up being used in practice.
Is there anything that you have found particularly exciting about your research, maybe something that you didn't think you would encounter, something that might inspire you to look into new avenues, or just anything that you want to highlight?
Yeah. This project, more than some others I've worked on, does pose some serious analysis challenges. The designs that we're working on right now for these adaptive facade mechanisms are pretty elaborate, and that makes them a little bit hard to analyze. So we could envision how to make it, and then we have to envision how to analyze it rather than the other way around. And that's been a fun challenge. I'm still kind of mulling over how we put together an accurate model of the behavior for what we're designing right now. And so it's a fun challenge, but I think it'll still take some time. And that's where student help comes in really handy, is to have extra minds to bounce ideas off of and try out different things. And we can work in parallel to try to come up with a method to predict the behavior of these designs that we're working on right now.
Yeah. And from my understanding, the mechanisms, you call them, or the designs that you're working on, they do a lot with efficiency and preserving energy, making buildings more efficient. Could you see similar mechanisms be used in other areas besides, buildings and architecture?
Yeah, I think that's absolutely true. And the mechanisms that we're designing are not necessarily even new. One of the approaches that we're taking is what's called bistability, which is a device that can either exist in a stable state in one configuration or in another, but everything in between is essentially unstable. It wants to snap into one configuration or the other. And the simple example that comes to mind is like a light switch. So if you flip it one direction, it wants to snap up. If you flip it, say, off, it wants to snap down. And so I would say some of the designs are already, in some sense, being used out there in everyday items. But our designs specifically take that to the next level and make it much more elaborate. There's a lot of different regions of this mechanism that all can have that behavior, so they all snap. So anywhere there's a need to move something through space, have it stay in one configuration without any additional energy, so any power to it, that's where what we're working on really could be used. So if those are your requirements, you just need something to stay in space in a certain configuration and hold itself there. That's essentially where this technology could be used.
What is another example of something like a light switch that you snap to one side of space, but you don't want it in the middle?
Sure. Yeah, one thing that comes to mind is maybe on a biological example, you can imagine like an inchworm that kinks its body into an arch and then it unkinks it to move forward. So that selective arch shape to straight, arch to straight creates a mechanism to move forward. So like I mentioned, my background is in robotics, and one of the challenges in robotics is coming up with new and creative ways to make robots move efficiently. And so that would be something that I could see being an avenue to explore. Can we create something that can move across a table very efficiently with low energy using this type of snap mechanism? Maybe one other example that comes to mind is in aircraft. If it's like a glider aircraft, so it's not actually powered, or even if it is powered, you're trying to save on energy as much as possible, having some of those what are called control surfaces on the wings that allow it to roll and pitch up and down, having those be this type of design where you lose some of the control that you might have by having those intermediate states, but you can at least have it pitch up and pitch down very efficiently using this type of snap mechanism. So maybe a couple examples along those lines.
Yeah. And I know before you mentioned you worked at Medtronics prior to your time at St. Thomas. What did your work there look like?
Yeah, I had a great experience working at Medtronic. I worked in a group that was developing a product known as a transcatheter heart valve. So normally when you have a heart valve replaced, it is a very invasive surgical procedure. You have to go on the heart-lung bypass machine, and there's a full open incision. What the transcatheter heart valve allows for is a replacement of the heart valve, but without that surgery. So it's delivered through a catheter, typically coming in through the leg, through the femoral artery. And then that catheter just snakes its way up to the heart. And there's a sheath over this device that we designed. And once that sheath is withdrawn, then the valve, the artificial valve, pops into place. So they're designed, at least the product we were working on is designed with a shape memory alloy, and it snaps open spontaneously then once the catheter is withdrawn, because it's designed so that at the temperature of the body, it's going to take on the shape that you want. Versus when it's chilled down, when you first load it into the catheter, you chill it down, and that allows it to maintain a small diameter. But then once it hits the bloodstream, it wants to really push out of that catheter and push its way into the position of the diseased valve. So that's the really innovative piece of this technology, is it pops into place and takes over function for the diseased valve once that catheter is removed. And there's no, other than the incision in the leg, very small incision. It's really a minimally invasive procedure. It's become very well established at this point, but back, 10 years ago when I was working in that area, it was still a relatively new technology.
Wow.
Yeah.
And to a non-mechanical engineering brain, that sounds wildly different to me from what you do now. Have you found that the research you did at Medtronics is totally different from what you're doing now in terms of like the process, what it looks like, the mechanisms that are used? Or have you found that your knowledge from, your background and what you do now is more intertwined than some of us might think?
I think it's the latter. I think I was able to retain some of the things that I learned and did at Medtronic in my research here at St. Thomas. The theme that I mentioned in my background is more in the controls and robotics space. And that actually does merge with the cardiac device space, especially in test environments. So when you want to test a medical device and you want to test it very accurately or with high fidelity to what the body would actually do, it does require some clever design of mechanisms and ways to make things move in space. And so that was some of my early research actually at St. Thomas, was seeing if I could enhance some test methods on implantable devices to make it more similar to what we call the in vivo environment, the inside the body environment. And that had, a host of challenges associated with it, but I think it was a good bringing together of my controls and robotics background with the medical device background that I had from Medtronic.
Yeah, that's super cool. And I heard that there's a new robotics lab. Can you tell us a little bit about that?
There is. So in the Schoenecker Center on South Campus, we have a space on the third floor. There was a generous donation by the Blattner family, and that allowed us to build out what we now call the Blattner Robotics Lab. And within that lab, we've also had some generous donations for equipment. And if you look in that lab, you'll now see, I would say, a very accurate representation of what you might find in a real-life automated environment,
That's
say
awesome.
Assembling products or putting products in boxes using robots. We can do all of that kind of thing in the lab. And I think it's going to be a really fun experience for students. They'll really learn a lot and then be able to hit the ground running once they encounter that equipment out in the real world.
Yeah.
There's still, of course, a lot to learn. Even if you were to master everything in that lab, there's always challenges that you encounter out there in practice that would take some additional on-the-job training. But for the most part, we try to make it a launching pad for students so that if they learn the robots and the systems in that lab, they would be really well positioned to work in that area after graduating.
That's awesome. What a cool thing to have.
We're very excited, and it's been a recent push this summer to get everything hooked up, everything running, still running some testing and putting some safety measures in place. You can imagine once automation equipment is running at full speed, you want to keep everyone safe around it. So that's what we're working on right now, is just kind of ramping up the speed, making sure all the safety checks are in place. But then we look forward to having students in there as soon as possible. Probably not this spring, but then looking at summer months and into next fall for sure, having maybe some classes, or at a minimum a few weeks of a class, come in there, learn some of the equipment, and really take away, I'd say 20% of the knowledge that's available, but that could solve potentially like 80% of the problems. That kind of 80-20 idea is what we're looking to solve with that lab. So
sweet. What does the difference in working in a private company lab look like versus an academic lab?
Yeah, that's a good question. I would say the biggest difference is the time horizon over which your work is looking. So in a lab that's in industry, I would say your time horizon is much shorter. You're really just focused on the immediate needs of your project, which is getting that product on the market. For medical devices, there's a whole approval process. So you want to be as efficient as possible, not take as many, tangent side research projects as possible, just being very efficient, again, looking towards your product, at most maybe the next generation product, which would be a few months after that one's on the market. You're already trying to get some enhancements in there. So that's the industry view, but then in the academic world, there's just a lot less aversion to risk. You can take side research projects, your time horizon is much longer. You're saying, well, this may not be useful in the next 5 years, but maybe in the next 10. And so there's just a lot less of an immediate need to apply what you're producing. So there can be more open questions, I would say, as you proceed through the research when you're in the academic world.
Makes sense.
Yeah.
And then this is a big topic right now, so we have to ask it. But how is AI affecting your field?
Yeah, it's like many would say, it's been a huge change. And I myself don't find my research using it extensively right now, but I know there are others that are really just jumping into it and seeing how it can best augment their research capabilities. Certainly, teaching has been another big change with AI. One of the examples I like to give in class when I talk to students about AI and engineering is there's really no substitute for knowing the language of engineering, though. So when you have a problem that you're trying to solve, it's just immensely more efficient to use an AI tool if you know the language. So if you know the right terminology to ask a question, you'll get back a very efficient, typically very accurate answer. In some of the early days, it was a little bit uncertain. And you always want to sanity check everything that's coming back to you from AI tools. But if you're really new to a topic or you don't know some of the specific terminology to apply to ask the appropriate questions in that, take the chat environment, then it can be just a bewildering journey through things that actually don't move you forward in your search for an answer. So that's what I typically tell students is that there's really no substitute for learning the language. You can maybe have the AI tool help with that even, but then you don't know what you don't know. So in general, I would say it's ever evolving, and I'm always looking for chances to incorporate it into the research. Some of my colleagues on that project that we talked about earlier are trying to integrate that into some of the optimization that we want to do for our designs. So it's an evolving question, and hopefully I'll have something even more interesting to say, even just in a year. It's such a rapidly changing environment.
Thank you so much for joining us, Professor Secord.
Thanks for having me.
To learn more about his work, you can find him on the St. Paul campus of the University of St. Thomas. The Professor Podcast is brought to you by the St. Thomas Libraries. I'm your host, Sarah Brings. The producers and library staff are Mary Davidson and Andrea Kepi. Thank you so much for our guests and to you, our listeners.